Everybody, today we are going to start talking about chapter 6 in thermodynamics. We're going to spend either 2 or 3 lectures on chapter 6, but the topic of chapter 6 is the second law of thermodynamics. We actually get into the majority of the calculations involving the second law in chapter 7, but in chapter 6 we're going to introduce the concepts. Second law of thermodynamics is an extremely valuable law of the physical universe, and yet it's something that a lot of people haven't really thought of quantitatively before, so sometimes it presents some issues where you have to think about the concept. The concept is not difficult, but it's something that you may or may not have really thought about before. So we're going to sort of expand our knowledge of how heat moves and how work is produced and what we're up against in the physical world. So I think I may have told you, but before I had this job, which has been this is my 21st year teaching, the man who taught before me had this job for 29 years. And so that means between the two of us, we have been the engineering instructor for 50 years here at Northwest College, which is kind of a crazy thought, but there you go. So it's quite a history, but his name was Don Fisher. And Don used to say of the first law of thermodynamics, which is the conservation of energy, that you can't get ahead because you never can create energy out of nothing. And then he said you will learn from the second law of thermodynamics that you can't break even. And then there's another corollary that he used to say, I won't write it down, but you can't even quit playing. So it's a stat game, and here we are anyway. So we have to keep playing, and we can't break even. So what are we to do? All right. Anyway, we keep playing because we can still work with the universe as it is, which is what we do as engineers. So the second law of thermodynamics has a couple of consequences. And there are 2 different ways to look at it. And in this chapter, we're going to start talking about refrigeration, because refrigeration is a kind of a cycle that it does not occur naturally, that has to be driven by putting work into it, which we'll learn about. But it tells us something about the second law of thermodynamics. So there are a couple of ideas that I would like to bring up. And the first one is every process moves preferentially in a particular direction. And even though you may not be aware of this, the first law does not tell us what this direction is. What I mean by that is if you have a hot cup of coffee and you put it in a colder room, so the T here is high, T here in the room is lower, heat will flow out. The first law will tell you how much heat will flow out, but it really doesn't tell you if the heat flows in or flows out. You need another law of, you could use common sense in this case, but sometimes reactions, it's not as clear which way something is going to proceed in. Another example is if you have an ice cube and the temperature of the ice cube is low, that means that the temperature of the surroundings is higher or hot, and what will happen is heat will go into the ice cube because of this temperature differential, and the ice will melt into a puddle of water of an equivalent mass. But once again, the first law of thermodynamics only tells us how much heat is involved. It doesn't tell us whether ice melts into water or water reforms into ice. And what you can see in these 2 examples is that what causes one reaction to happen and the other reaction not to happen is not within the system itself, it's within the surroundings. It depends on where it is. So you take that same hot cup of coffee, and if you put it in a very cold room, you're working out in your shop, you don't have an insulated cup, you're working out in your shop and you're doing some stuff and it's 22 degrees in your shop, your coffee's going to cool off very quickly. If on the other hand you're in Phoenix and your shop is at 92 degrees and your coffee's at 103 degrees, it's going to cool off less quickly, and it's only going to cool off to about 92 degrees. It's never going to go below that. So it doesn't have anything to do, it has something to do with the system, but the direction and the speed with which the heat transfer occurs depends on the system and the surroundings. So that's kind of the big deal. The system plus the surroundings determines the direction of the reaction and the speed of the reaction. Okay. So we talk a lot about heat in this particular way. Now, if you think about it, here's what we're going to have to do. Now, that doesn't mean that we are victims of reality. If you have a refrigeration unit, so let's just talk about a refrigerator. How does a refrigerator work? Well, you have an insulated compartment. So there's lots of good insulation in it. And there's a system of refrigeration fluid moving through coils or in some way around this refrigerated space, which is T sub L, low temperature. And you reject heat from T sub L to T sub H. Well, that is backward, isn't it? In other words, heat doesn't move from a low temperature region to a high temperature region unless you drive it. And the way that you drive it is by putting work into the cycle. And that's the sort of thing that's predicted by the second law of thermodynamics. How much work it takes, how cool you can make that refrigerated space, how much heat is going to be rejected to the room. But if you, I guarantee, so here's another one. How do you know that work is being put into a system? Well, most of the time the work that we put into a system is in the form of electrical power. And you can, this is my version of a three-pronged electrical plug. That means that you plug it into the wall and you get electricity out of the wall. And I will guarantee you, if you unplug your refrigerator, it will quit working. It won't quit working that minute. You're not going to lose all your food like in 1 minute, but it will quit working. That seems intuitive, but we really don't have a law. The first law of thermodynamics does not tell us that. It just says heat moves out. But why does heat move out? How fast does heat move out? We don't know those answers until we start talking about the second law of thermodynamics. Okay, so one concept that we need to talk about is a word that you have probably heard before, but it is called a reservoir. And what a reservoir means, there are two different types of reservoirs. There is a heat source, which puts heat into something, and a heat sink, which takes heat away or accepts heat that's rejected from an engine or some sort of a process. The idea of a thermal energy reservoir is the reservoir is big enough or big or I'm just going to say big in quotes because I don't really have another good word. So it doesn't mean necessarily physically big, but it's big enough to accept or supply all the heat of the reaction or the process, which would be a more general term, without changing temperature. Okay, so if you have a house and it's 40 degrees outside, and you like to keep your house at 72 degrees Fahrenheit, okay, and you have heat seeping out of your walls, and you have heat moving out of your windows, and then I don't know, you guys were probably more obedient children than I was, but I was always running out of my house and leaving the door open, and my dad was always yelling at me, trying to heat up outside. Well, that's never actually going to happen, is it? I mean, this little bitty house in the outside is never, even if my father put the furnace on full blast furnace setting, if I left the door open, this temperature of the outside is never going to significantly change based on all of the heat that we put into the house, right? It's just not going to happen. In that way, this is a heat reservoir. And in this case specifically, it's a heat sink. Now, another example of a heat sink that I think is fairly dramatic involves nuclear submarines. Okay? Any nuclear reaction, but I like nuclear submarines because it's really specific. The nuclear propulsion on a submarine generates a tremendous amount of heat. Okay? Why does the nuclear submarine not melt? Why do the people not die of heat inside the submarine? The heat sink of the ocean. Because the ocean is very large, right? And water has a very high specific heat. That's also like why if you burn yourself, if you run cold water on the burn, it will carry away a lot of heat. And if the value is called C sub P, which we've talked about a little bit. But basically, it carries away heat very, very well, and especially when the water is circulating. That's why nuclear plants, like there was the one in Japan that melted down a few years ago. There was the one in Chernobyl that melted down in '86. There's the one that almost melted down in Pennsylvania back in 1979. What happens in all of those cases is the water is somehow no longer circulating to the nuclear core because the nuclear reaction produces a lot of heat, needs to be taken away. Air does not have enough specific heat, or it doesn't have the capacity to accept heat, and it starts to heat up, and then everything starts to melt down. So that's why the water part is important. So that's also why nuclear submarines work very, very well. But if you took one and put it up on land, on an island somewhere, it would not work very well at all. So, well, it might work well until it melted down and everybody died. But basically, the water's the thing, the heat sink. So the core generates lots of heat, but the ocean is very big. And when I said big, I mean that in two senses. That's what a heat sink is. It can either be very big in the sense that it has a big area, or it can be very big in the sense that it's that you're immersed in something that has a very high specific heat and is able to accept a lot of heat. Okay, so that's another thing. Like in the radiator of your car, when it's very, very cold, you might mix antifreeze plus water at 50-50. Okay. What really happens is antifreeze actually has a lower specific heat than water. Water is better at accepting heat than antifreeze, which is ethylene glycol. However, ethylene glycol depresses the freezing temperature of the water in your engine. So if you live here or somewhere very cold, and it's 20 degrees below zero, what's the freezing temperature of water? It doesn't matter where you live, but what is the freezing temperature of water in centigrade? 0, exactly. So does it get below 0 degrees centigrade here, which is 32 degrees Fahrenheit? All the time, right? So you don't want your car to freeze up, so you put ethylene glycol in it. It depresses the freezing point so that the water mixed with antifreeze remains liquid and is therefore able to carry the heat away. But if you put straight antifreeze in your car, it actually it is less able to remove the heat. But you're looking for the two. You're looking for removal of heat and not freezing in your engine. So, a couple of different things. All right, so when we talk about thermal energy reservoirs, that's what we're talking about, heat sinks and heat sources. The best heat source that I can think of, I mean, there's a zillion of them, but a heat source, once again, is something that produces heat without changing temperature. And the thing that really comes to mind first is the sun. You know, I mean, the sun just produces and produces and produces. It's an ongoing nuclear fusion reaction, and it produces energy. And for the human lifespan, and probably for a planetary lifespan, it will not change temperature. In the scheme of things, that may or may not be true, but over the course of human life, it is definitely true. All right, so the basic idea then, and we'll break this down a little bit in a little bit more scientific ways, the basic law of second law of thermodynamics, one of the things it tells us is heat moves from a high temperature reservoir or from high temperature to a low temperature unless it is driven, and by that I mean work is put in the opposite direction. Okay, and reactions occur not only in a particular direction, but also at a preferred speed. And these two ideas are tied into something you may remember from chemistry, which is the idea of irreversibility. If things tend to move in a particular direction, that means that they're more likely to move this way than this way. A truly reversible reaction, which is an ideal, it's a theoretical ideal, a perfectly reversible reaction would have an equal tendency to move one way as it would the other. So in other words, hot coffee might heat up, might cool down, we don't know. So as things approach reversibility, nothing is truly reversible, but as they approach reversibility, our theoretical limits, I guess is what I would call it. And as they approach reversibility, they become very slow. So you have to have a very small delta T, and it also, you have to have a ton of time. So, and once again, it's not something that we ever actually reach, but it's a theoretical ideal. All right, so there are two appliances or two types of devices that we are going to be talking about, and there are two statements of the second law. But today we are just going to talk about one of those, which is called a heat engine. The purpose of a heat engine is to produce work from a high temperature reservoir. So, or it could be a reservoir, it could not, it could be just a high temperature area. But for example, if you have a car and you want the car to move down the road, you do that by combusting gasoline or diesel fuel in a cylinder. So the cylinder is at a very high energy state, and you exhaust spent fuel and combusted the products of combustion to your exhaust stream, and in the process you generate work done by the car. Another type of a heat engine could be a turbine being run by a boiler. You can actually kind of think about like heating systems, not heat pumps, but old-fashioned furnaces you can think about in this way as well, although their purpose is to just move heat from a high-temperature reservoir, which would be the boiler, to a low-temperature reservoir. So if we just talk about the kind of a heat engine that produces work, this could be a turbine, for example. And the way that we draw this is the stick figure version, but basically you have a high-temperature reservoir where we have Q sub H. So T sub H means high temperature. Q sub H means the high temperature heat. And from this particular heat source, we move heat into our heat engine. And by doing so, we are able to get some work out. But now the consequence of living in the physical world is not only the high temperature reservoir is important, but also the low temperature reservoir. In other words, we have to exhaust some of that energy to a low temperature reservoir in order for work to occur. Now, this heat engine is said to perform in a cycle, which means that we're not spending the fluid. So like this might be water circulating or a boiler that's circulating water in order to produce heat or work in this particular case. So we have some stroke where we're losing heat, some stroke where we're gaining heat, and we have work done in between. Well, if you look at the first law, if it's a cycle, that means that the final condition or state, let's say the final state, is equal to the initial state. In other words, we circulate our working fluid, whatever that is, back to its original conditions. So that means that delta E of the system is going to equal 0 because we're at the same energy state at the beginning as we are at the end. So if we look at the first law of thermodynamics for a closed system, and this is equal to 0, we then that Q is equal to W, and as we see, we've got Q in minus Q out is equal to the work. So in other words, we take heat from the boiler or the high temperature reservoir into the engine, we generate work, and we expel some heat. And that work is actually the difference between the heat that we brought in and the heat that we take out. So can you minimize this heat? You can minimize it, but it's never equal to 0. And the reason for that is that whenever you have a T sub H, what does T sub H tend to do? It tends to move heat from T sub H. Q moves from T sub H to T sub L. So that means that as long as T sub L, the surroundings, is less than T sub H, the source, we will eject heat. That means Q out will always be greater than 0. Okay. Now you can minimize this in order to increase efficiency. Sometimes it's worth it and sometimes it's not. As engineers, we also have to consider the fact that sometimes if it's very expensive to get a small incremental of heat turned back into work, it may not be worth it. So we have to weigh all those factors. But you can never make it be exactly 0. The only time it could be 0 is a theoretical case, obviously, if and only if the cycle is reversible, which we know is not ever possible, and T sub L is absolute 0. Okay? And that's because we can't reach a temperature below absolute 0. So if you look at this, you could always think about, well, what if I could pull down my temperature a little bit lower? Then this could become my Q sub H, and I could expel this just a smaller amount of Q sub LL. So as long as I can expel down here, I'm not going to have a 0. So if this were T sub L, we're equal to absolute 0, which once again is another theoretical ideal or approach, limit, then we're always going to have a possibility that we could have run a little bitty engine on our exhaust stroke and made some more heat if the temperature were lower. So we have to have two things. We have to have a completely reversible cycle expelling heat to absolute zero. That's the only way that we can ever get Q sub H would be equal to the work out. Okay? But if and only if. And neither one of those things will ever happen, so it's just something that you can approach. Right? So, as engineers then, we have another question to answer, and this is the last point that I'll cover. If the work out is always less than the heat that we put in, which we've just determined has to be true, how can we measure, since it's never 100% good, how can we measure how good our process is? And for a heat engine, this measure is called thermal efficiency. And so what we're really looking at is what percent of the heat we put in is turned into work. So thermal efficiency is called out by the variable NTH, and NTH is defined then as the work that we get out of the heat engine divided by the heat that we put in. Now these have to be in the same units, but they could be in kilojoules, they could be in foot-pounds or whatever. We could also define it as power out over the rate at which heat comes in. All right, well, looking back at our little original heat engine cycle, we can see that work is equal to heat in minus heat out. So we can rewrite this, I'm just going to write this side of the equation, as heat in minus heat out divided by heat in. And you can write it in this form, or you can separate this as Q in over Q in minus Q out over Q in, like that. And anything over itself is 1 minus Q out over Q in. So another way to write the thermal efficiency is this. So this is the basic statement, and this is a more functional statement usually. Now, what that means is this number, first of all, this 1 is just 1. This number, Q out and Q in, are always going to be positive quantities. So in other words, a positive divided by positive will be positive, so it's 1 minus some positive number. That means that NTH will always be less than 1.0, or you can call it 100%. It also tells us that the only way that the thermal efficiency could be 1 or 100% would be if this term were equal to 0. That means if we were not expelling any heat at all, or if the heat in were infinite, right? It's the only way, and neither one of those things is going to happen. All right, so at this point, I am going to write the first word statement of the second law of thermodynamics, and then we will call it a day. The second law of thermodynamics, as applied to a heat engine, is called the Kelvin Planck statement of the second law. And you may remember Lord Kelvin. Kelvin and Planck were both scientists a couple hundred years ago. But it says it is impossible. So it tells you what it can't be. It doesn't tell you what it is. But it tells you that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay. That refers back to our drawing of the heat engine. And what it's saying is that if you're only exchanging with a single heat reservoir, if you just have T sub H bringing you Q sub H, you will not get work in a cyclic or cyclic device unless you are also expelling heat. So if Q out is equal to 0, there will be no net work. And that's the statement, the Kelvin Planck statement. So that goes along with the other things that we've said today. All right, so does anybody have any questions at this point? We do not have homework posted for Chapter 6 yet. This takes us through sections 6.1, 6.2, and 6.3. When we come back on Tuesday, we'll talk about the second law of thermodynamics for refrigerators and heat pumps. And then Thursday, we'll finish off Chapter 6. And I will post your homework before then. So you guys have a great day. We'll see you next time.